Good afternoon, everybody. Happy Tuesday. So I'm not sure if you actually were able to hear that saying that this meeting is being recorded. So I guess from now on WebEx, I can't record to my desktop and upload it up onto YouTube. So it saves all the videos. If you go to the WebEx area, which you can watch the videos, these live videos, it's going to have the recording saved over there from now on. So I'm not sure what happened, but I think they might have updated something recently to not allow me to use YouTube probably for video, which is fine. Maybe it's better off this way, so it's more official, I guess. So did make that announcement on Discord about that. So but just from now on, the videos will be saved on WebEx from now on, not YouTube. So I apologize for the inconvenience, but that's just how it is, I guess. So um, I'll probably have a new assignment up around Thursday or so this week. It'll be just doing bucket sort, radix sort, and I'll have maybe some conceptual questions where you have to, given this circumstance, it's just one of those conceptual stuff I'll have as well on there. But of course, you have to trace out bucket sort and radix sort. Anyway, let's go ahead and just sort of continue from last time's lesson. So it's last time I pretty much just went over binary search trees. So for the most part, nothing really too surprising how this works. So doing a find and insert is relatively similar or the same idea like from CS302. So it shouldn't be anything too complicated as to how that works. Now, the deletion part I went over last time, I think I might have just sort of got myself overwhelmed a little bit with that. So I'll talk about the deletion content once we go over how to delete from AVL tree, which is the next sort of content for this class. Because remember, with binary search trees, the runtime to do a find or insert, even deletion for that matter, all depends on the size of the tree, or not the size, but the height of the tree. So if the height is log of n, then every operation, find, insert, deletion, all takes O of log n. Now, if it's not balanced, they could take O of n in the worst case. It could go up to that much if, let's say, you don't have a very nice balanced tree. So the purpose of an AVL tree is to have a nice balance or to kind of force this balancing in our binary search tree. So let's go ahead and start these new nodes over here. AVL trees. So I guess the name comes from the researchers who came up with this strategy for this tree. I think one of them had last name A, one had last name V and L. So that's sort of how a name came together. But basically, it's just a self balancing binary search tree. So it's really going to be the same sort of work as a regular binary search tree, except we do a little bit of extra steps we do whenever our tree is not balanced. That's sort of the idea. So what we do is on every insertion and deletion, we would perform, I guess, rotations on the tree. So what we do is you do rotations as a way to kind of fix the imbalance. So the idea is that the real, I guess, the only real issue with an AVL tree is that every node maintains a counter, or I guess, a variable, I guess a counter that denotes its height. So basically, this is sort of the only add-on to AVL trees is we have to have every node has to maintain its own height. And it's going to be a counter. It updates by a certain amount. I guess it's not really a counter, but it's going to be maybe an integer, I guess. I'll say integer instead. So it maintains an integer that denotes its height. So we have to maintain this value in every single node. And if a tree gets very large, this number can get pretty large as well. So this is the only real sort of issue with AVL trees. We have to maintain this in order to really be able to quickly sort of fix the binary search tree and be able to do rotations properly. So the idea to be balanced. So in order to have a balanced binary, I guess binary search tree, any tree for that matter, but I'll just say binary search tree, but it could be applied to binary tree as well. So in order to be balanced, the difference, so I guess if I say for each node, the difference of the left and right subtree height is off by at most 1. So if we have this maintained, or if we have this property, then our tree is going to be balanced, or balanced enough. It doesn't have to be perfectly balanced, but this property will make it balanced enough. So we'll, of course, prove later on as to why this has to be balanced enough, but as long as we maintain this property, we're okay. So that's basically the sort of the preliminaries to AVL trees. We maintain some integer for every single node that denotes its own height because we don't want to have to constantly recompute the height every single time. If we do that, the runtime for this gets very slow. So just maintaining that variable in each node that stores the height is a very quick way to look up the height of every single level in the tree. You have to maintain this property, and then we have a balanced binary search tree. So now we want to go over rotations. So this is going to be the key to really maintain a balanced binary search tree. So red-black trees also have the same type of sort of work. A rotation has to be done to fix the imbalance, which will cover red-black trees later on. So consider the following tree over here. So we're going to have K1, which will be just a node in our binary search tree. Just over a little bit to the left. So we have K1, we have K2, which will be 2 nodes, and we're going to have the following subtrees. Try to draw this if I can. This is actually a little bit, I always mess this up, but this triangle X is going to be an entire subtree. It's going to be. And then we have K2 has its own subtree. This is always kind of hard to draw. And we have another subtree over here. So this is a possibility for an AVL tree or for a binary search tree. And we have this situation. We see that it's a little bit lopsided on one side. So K1's right side has more nodes than the left side of its subtree. So think of this binary search tree as like a scale, old-fashioned scales where it's sort of one side is kind of a little bit sort of heavier. We want to somehow rotate this by sort of want to rotate this tree to have the right side move up a little bit and left side moves down a bit to sort of balance the scale. So this situation here, this will be a case we have to do a left rotation. So you have to left rotate K1 because K1's right subtree is larger than left subtree. And for K2, K2's right subtree is also larger, so a single left rotation will fix this problem. So a rotation is actually a very simple process. All we have to do is the following. So I'll go ahead and I'll sort of draw this here and I'll go ahead and I'll erase it, but this is all we have to do. So we're going to basically take, we have these two pointers here. K1's right pointer from now on is going to actually point to K2's right side. You have to update that pointer. So whenever you rotation, we have to maintain, so we gotta know this is where the imbalance occurs, and we have to also have these two pointers that points to K1 and K2. So over here, what happens is we set K1's right pointer to point to K2's left, which will basically create this situation. And since we know that this Y subtree is on the right side of K1, it's not a direct, right child, but it's on the right side somewhere. Doing this is not going to violate the binary search tree order because, well, Y is on the right side of K1, so doing this is not going to mess anything up. And then we're going to update K2's left pointer to, I guess, sort of point to K1. So since K2 appears on K1's right side, that means K2 has to be larger. So if we have K1 be on K2's left side, so K2 will now be the parent in the situation, well, that also does not violate the binary search tree order. Because K2 was on the right, K2 has to be larger. So if K1 is K2's left child, it still does not maintain a binary, doesn't break binary search tree order. And after that, we return K2 up to the parent node. So whenever we insert into a binary search tree, we always return pointers up to the parent that will catch the child node. So we're going to just sort of do two pointer assignments, turn K2, which will cause K2 to be lifted up above K1. It's kind of hard to, but basically the idea is we just sort of set K1's right to K2's left. K2's left will point to K1 and return K2, which will lift K2 up. K1 falls below, and X will still be on K1's left side. That will not change at all. And then K1's right will be Y. Then K2's right will still be Z. It's kind of not really drawn to scale, but we do examples of it, it'll make more sense. But the idea is, what happens is that we do a left rotation, then K1's right child will get lifted above K1, and K1 will fall below with X. Z will still be on the right side, but you sort of have to set Y to be K1's right side. So it's simply just two pointer assignments and return a different pointer up to the parent. That's all there is to it. So we left rotate, it kind of fixes imbalance. We sort of have to fix the scale, sort of. That's what we do for left rotation. So we'll do examples of this on actual AVL tree, but that's sort of how left rotations work. So let's go ahead and now go over a right rotation. So in this case here, we're going to have K1. We have K2 over here. That. And then we're going to have X subtree, just like that. Then we're going to have Y there. And we're going to have Z over here. Hard to draw this up, but in this situation, we have it where left subtree is larger. What's going to happen now is we see that we have an imbalance over here. We have to look at the left subtree of K1. So since K1's left subtree is larger, we check K1's left subtree, which is K2, and since K2's left subtree is larger, we have to right rotate. Now we'll cover double rotations later on, but let's go over just the basics of rotations for right now. Anyway, to fix this problem, very similar to a left rotation. All we have to do basically is once again, we have to set K1's left to be K2's right. So K2's right will contain this Y node. So we set K1 its left to simply point to K2's right. A simple pointer assignment because we have a pointer pointing to K1, we have a pointer pointing to K2, so very similar, very simple to actually to set that. And then we're going to set K2's right to point up to K1. So once again, since Y, that whole subtree, is on the left side of K1, if we set K1 to directly point to Y, it will not violate the binary search tree order. And also, if I have where K2 would be the potential parent of K1, if K2's right points to K1, it also does not violate the binary search tree order because since K2 is larger, sorry, K2 is smaller, I'm sorry. So if K1 appears on K2's right side, it's still the same idea because K2 is less than K1. So if K1 is a right child of K2, that does not break anything. Binary search tree order is still maintained. So we use simply two pointer assignments and then return K2 pointer up to the parent. So potentially K1 could be the root or K1 could be a subtree within our binary search tree. Returning K2 will assign the parent of K1 to now be, so K2 is the new child of K1's parent. So what happens is return K2, K2 gets lifted up basically. K1 falls below, and so does X as well. Of course, Z will still kind of fall below. And then Y is now going to be K1's left subtree. They have a left rotation over here, or side right rotation. This was sort of my my sort of Bushworld Rick and Morty sort of drawing. Every single frame in that episode has different sort of animation. Same idea here. So, but the idea is that for rotation, we have to update two pointers, K1 and K2's pointers, and then return a new pointer up to the parent, which will lift that subchild up above. So lifts K2 above K1 just like that. So that's basically how we do right rotation. So now we'll do some examples on this, but this is going to fix the imbalance. If you notice on both pictures, K1's left side was larger. We sort of lifted K1's left side up and K1's right side down a little bit to kind of fix that balance, to fix the imbalance basically. So that's what we have to actually do. So that's what we do for this right rotation and for left rotation as well. So now let's go over actual examples and see how we actually can implement an AVL tree. So, or how we can actually visualize how all of this actually works. Let's do some examples. So for this first example, I'm going to insert the following elements in this order. Insert 50, 5, 75, 20, 60, 85, 80, 90, and 100 in this order. So these will be our key values stored in every single element in our AVL tree. And we're going to just try to insert them in a way which will still preserve our binary search tree. So we first insert 50. So we have an empty binary search tree, so inserting 50 will just have 50 at the root. I'll put a green number here which denotes the height of this node. So we're going to have every single node has to maintain a key and a value. Now for the value part, we'll just have it where we're not going to really consider the value really. We want to care about what's the search key, and the height is what's going to be really important in this situation. Okay, so we first inserted 50, no problems there. So now we're going to have to insert 25 next. Okay, so using the same sort of method inserting to binary search tree, we first check 50. 25 is less than 50, so 25 has to appear on 50's left side. And since there is nothing on the left side of 50, we're going to create a node over here, 5, with the height of 0. So after we insert into our AVL tree, we return the pointer back up to the parent. So 50 will now see that its left subtree has a height of 0, and the right has a height of -1. So there's no imbalance here. And we're going to have to update the height of 50, this node, to be 1, because we have to take the max of its two subtree heights. So basically, an empty tree has a height of -1. So the left side of 50 has a height of 0, the right side has -1, so therefore there's no imbalance. We take the bigger subtree, add 1 to it to get 50's height amount. So now let's insert 75. So you always start from the root first, and 75 is bigger than 50, so 75 has to appear on 50's right side, and there's no child here on the right side of 50, so we're going to create that child right there, insert 75, and its height will of course be 0. It's a single node, no children. So then we return this back up to the parent. So parent now catches the result. So now 50's right subtree has a new height of 0, and the left subtree height of 50 is also 0, so there's no imbalance. And then we have to take the max of the two subtree heights and add 1 to it. So in this case, 50's left and right subtree both have a height of 0, so the max will be 0 here, plus 1. 50's height would be 1. Okay, so far, nothing has gone wrong yet. Let's go ahead and now insert 20 into our AVL tree. Okay, so we first check from the root, and 20 is less than 50, less than 25, and 25 has no child on the left side, so we have to insert 20 to the left of 25. We insert 20 over here with the height of 0. And then once we insert, we have to back up, return back up the tree. So we have to update all the parent heights as well. So as we return back up, we check 25's left subtree has a height of 0 now, and 25's right subtree has a height of -1, so there's no imbalance there. We take the max of those two between 0 and -1, and the larger subtree of 25 is 0, so plus 1 will make the height of 25 to be 1. We return up to the parent of 25 back to 50, and at 50 we check, okay, so 50's left subtree has a height of 1, and 50's right subtree has a height of 0. There's no imbalance, so you have to take the larger of the two, which will be this subtree, add 1 to it, which means that this tree has a height of 2. We simply take the two subtree heights of every node, take the bigger one, add 1 to it, and assign that to our self, basically. So that's how we update the heights like this. So no issues there. I'm going to go ahead and sort of stop Discord because I'll just stop Discord right there. Anyway, so now we inserted 20. Let's go ahead and now insert the next element into our AVL tree. We insert 60 next. Okay, so 60 is, we first check with the root. It's larger than 50, less than 75, and there is no left side of 75, so we're going to insert 60 right over here using our normal binary search tree insertion. So okay, fine. So we insert 60 there, and it has a height of 0. Return back to the parent of 60, which would be 75. We check. 75's left subtree is 0. Its right subtree is empty, so it's -1. Difference there will be 1, so there's no imbalance issue. And we're going to update 75's height to be 1 because we have to take the two subtree heights of 75, pick the bigger one, add 1 to it, that's going to be the height of 75. Okay, let's go back up to the parent of 75, so 50. And 50 has two subtrees, they're both height 1, so we're good. And the height of 50 remains 2 still, so we're good. That's going to be the end right there. So no problems yet. So eventually something will go wrong, but I guess not just yet. Now we're going to insert 85 next. So 85 is bigger than 50, bigger than 75. 85 has to go right over here with the height of 0 once again. And this causes no problems because, well, as we sort of return up the tree, every single time none of the parents will have any imbalances and their heights will remain the same. So that doesn't really cause any issue. Okay, let's go ahead now and insert 80. So insert 80, once again, we'll go through this entire process. It's bigger than 50, bigger than 75, less than 85. So 80 has to go over here with the height of 0. So now return back to the parent of 80, which would be 85. We check its left and right subtree heights. It has the left subtree of 0, right subtree negative 1. So there's no imbalances there. But we're going to update the height of 85 to now be 1 because we have to take the max of its two subtrees. The max will be 0 plus 1 becomes 1. Then return back to the parent of 85 to 75, and we check 75's left subtree is 0, and the right subtree height will be 1, so no imbalances there. Take the max of its two subtrees, so for 75, the right subtree is larger, so we're going to take that amount and add 1 to it. So 75 has a height of 2 from now on. Then we go up to the parent of 75, which will be 50, and we see here that, well, for 50, its left subtree height, which is this node, is right here, height of 1, height of 2, so there's no imbalances because the difference is going to be off by 1. So there's no problems here. And we take the bigger subtree, add 1 to it, and store this as a 3. So far, everything is kind of okay. There's no problems yet. Now let's insert 90. So 90 is bigger than 50, bigger than 75, bigger than 85. So 90 has to go over here. Height of 0. And this will actually cause no problems. It's going to return up the tree and everything will be reassigned, but nothing will change. So there's no imbalances once again over here. Everything is still just fine. So now let's go ahead and just insert our last element, 100, which I think this will finally cause a problem. So 100 is bigger than 50, bigger than 75, bigger than 85, and bigger than 90. So 100 goes right over here with a height of 0. Go ahead and zoom out so we can see this. Okay. So now we return up the tree. So for 90, its left subtree has a height of -1, right subtree has a height of 0. So we're going to have no problems there, but we're going to have to update 90's height to be 1 because we take the max of its two subtrees and add 1 to it. So that's going to be the case there. I go ahead and return up to the parent of 90, which is going to be 85. And we see here for 85, its left subtree is 0, right subtree is 1, so there's no problems there. And we're going to update 85's height to be 2 because we take the larger subtree of 85, add 1 to it. Now 85's height will now be 2 from this point on. We return back up to the parent. And the parent, well, we have these two subtrees. So we're going to first compute its height, which will be now 3. But the problem now is 75's right subtree is going to be 2, and the left subtree has a height of 0. So we have an imbalance now. Because notice 75, the right subtree, height of 2, left is 0, the difference of its two subtrees now will be exactly 2. It's larger than 1, so we have an imbalance. So right here, we detect an imbalance. So now we have to fix this imbalance because we don't want to have too much of a lopsided tree. So we see here, okay, we have to check, well, which subtree is bigger? Obviously, the right subtree is bigger. So there's a larger subtree over there, which implies we have to left rotate 75. But we first have to check, do we have to rotate these subtrees right here? So since 85's right subtree is bigger, we do a one single left rotation. So we found the imbalance. So as we turn up the tree, the first instance where the left and right subtree heights differ by more than 1, that's going to be our imbalance. And we see here that the 75's right subtree is larger, so a single left rotation will fix this problem. Let's go ahead and left rotate this. I'm going to actually copy all of this. Over here. Let's go ahead now and sort of fix this imbalance. So, in this situation, so for rotations, how does it work? Well, we're going to first have to set 75's right pointer to point to 80. So we're going to erase this and have it point to 80 as our first step. Very simple single assignment of a pointer. And then 85's left pointer is going to point up to 75. So now 85 will be the parent of 75 from now on. And then we're going to return this 85 node. So let me go ahead and actually, maybe I can see if I can, I'm going to try to see if I can sort of do some more interesting stuff here. So I'm going to do the following. We first do this. Actually, no, I'm not gonna, I'd rather just do it step by step for note taking, so never mind. This will cause more confusion. Okay, so we first make those two pointer assignments, and then we're going to return 85 up to the parent. So 50 is the parent of 75. 50's right child was 75. We're going to return 85 actually now. So 50's right pointer is going to now point to 85 from now on. We're going to return 85. So the result of this is going to be the following. We're going to have 50 over here. Sort of going to be over here. 50 over here. And this side does not get affected. So we'll keep the same nodes over here. 0, 1. We'll have a 3 here still. And an 85 gets returned. The height of 2. And then 90, 100 remain the same. Those will not get affected whatsoever. And then 85's left child will be 75. The height of 3. 60 for its left. Remains unchanged. And 80, right side of 75. Like that. And then we still have this red pointer still pointing here, and the blue pointer points over here. So we have to update the heights of that blue and red node. So here we check that we first have to update this red node. So it will now be a height of 1 from this point on. And then this will have a height of 2 still. Return a height up to 50 will be 3. And we see that now we have no imbalance issue. Because we see here, for every single node, the left and right subtree heights will be off by no more than 1, as we can see over here. So everything works out. So simply, it's just you have to modify, sort of reassign a few pointers, return a new pointer or a new node up to the parent, and that's it really. That's how rotations work. So any issues on that? Before we go on to another example. I think we're probably okay. All right, so that was our first example. This was a left rotation example, so I'll put this over here, write it here more formally. You have to left rotate. Let's go ahead now and discuss example for right rotations. Let's cover this one next. So I'm going to go ahead and I'll try to zoom in and back to the way it was before. Let's go ahead and make a new example. So let's go ahead and now try one where we may have a different type of rotation. So let's try the following. So I'm going to insert the following elements into my AVL tree. I'll go a little faster on this one since we kind of may have an idea of how this works, but just another big example just to show this example like this. 20 and 5. Go a little quicker on this one. So again, we have to insert, we're going to build in a binary search tree. You first have to insert 50, the height of 0. We insert 25 next, which we go over here. Height of 0. 75 here. 0, and of course you have to update this height to be 1. Then we insert 80 next. So 80 goes over here. Height of 0, which will cause this update to height of 1, 2. And we see there's no imbalances to worry about here. Insert 30, less than 50, larger than 25. So 30 has to go over here. Height of 0, update this to a height of 1, and the root will still be height of 2. And there's no imbalances because every level, the left and right subtree heights will be, I put this over here so it's so confusing there. So anyway, we have no problems here. Every single node's left and right subtree height will be off by no more than 1, so we're good. Let's insert 20 next. 20 is less than 50, less than 25. Put 20 over there. Height of 0. And if you go up the parents sort of nodes, nothing updates. So we're here, nothing is wrong still, so we're still fine. Let's insert 22 next. The 22, less than 50, less than 25, larger than 20. So we're going to put 22 right over here. 2 goes right over here with a height of 0. You have to update the heights accordingly. So this will be a height of 1, height of 2, and a height of. So as we turn up, we have to update the heights accordingly by simply checking the left and right subtree heights. And the bigger of the two, we add 1 to that, that'll be the height of that node. And again, we see there's no imbalances because every single level, the left and right subtree heights will be off by no more than 1. So there's still no imbalances to worry about here. And let's insert 10 next. So 10 is less than 50, less than 25, less than 20. So 10 goes over here, height of 0, nothing updates. Everything will remain the same. As we go up the tree and insert and update heights, nothing changes. So we're good. Now we're going to insert 5, which will cause our problem. Zoom out a little bit here. Insert 5. Well, less than 50, less than 25, less than 20, less than 10. So 5 has to go over here. Height of 0. And we go up the tree. So 10 has a height of 1 because its left subtree is 0, right subtree is -1. The bigger of the two is 0. Add 1 to it. 10 has a height of 1 now. Return up to the parent of 10. So at this level for 20, there's no imbalances because 20's left subtree has a height of 1 and 20's right subtree has a height of 0, but we'll update its height to be 2 because we take the bigger of the two subtrees, add 1 to it, which will give us the height of 20. And then we go up to the parent of 20 is 25. So 25, well, in this case right here, 25's left subtree is 2, right subtree is 0, imbalance is detected right there. The very first instance we see the imbalance, that's where we have to rotate and fix the tree. So whenever we insert, we turn heights up accordingly, and we see right there, we have the imbalance issue. Okay, so we have to look at this node as well. So since 25's left subtree is bigger, we must maintain a pointer that points to that node as well. And since that blue node's left pointer, a left subtree is larger, we have to do a single right rotation to fix this problem. So very simple case once again. Let's go ahead and sort of fix this problem. Let's go ahead and do our rotations again. Very simple process, similar to the last one. Let's go ahead and copy this and I'll put it below over here. So to fix this problem, well, once again, how do we fix this? Well, we have to basically set 25's left pointer to point to 20's right, like that. So this will not violate the binary search tree order. We first have to do that. Then we have to set this blue node's right pointer to point to 25. And then return 20. So 50, its left pointer was pointing to 25. It will now point to 20. We have to return 20 essentially. The result now is going to be 50, height of 3. And the right side remains the same. Nothing changes over here. And then the 20 goes up. And then we're going to have a 25 will fall below. 30 falls below. This remains unchanged. And 25's left will be 22. Remains unchanged as well. And 20's left will have a 10. Remains unchanged. And then 5 remains unchanged as well. So we have this red pointer pointing over here, and the blue pointer is over here. Now we have this part where this rotation is now done. We have to update these heights. So 25, its left and right subtree heights are both 1. So the height will now be 1 for this. And 20's left and right subtree heights are both 1. We'll make this a 2. And oops, it's supposed to be 1. And return 20 back up. So 50's left pointer will now point to 20, and 50 remains height of 3. And now we see here we have no imbalances to worry about. Everything is all good. So we have off by 1 at most at every level, but we don't have any node that has the left and right subtree height off by more than 1. So now we're balanced. That's the result. So we had a right rotation in this example. Like that. So now I think I'll probably I'll do 2 kind of quick examples over here just to kind of finish off AVL trees today. But any issues or concerns so far? It's relatively, I think, the same concept from 302. I'm not sure. I know I covered this in 302, but just to kind of recap, because we're going to be using this concept for red-black trees, which I don't cover in my 302 class. But anyway, let's go ahead and do sort of 2 kind of relatively faster examples just to finish off AVL trees. So right now we covered examples where we did a single rotation. So now we're going to do examples where we have a double rotation. So right now, we looked at so far, the tree was so what happened was the left subtree's left was larger, and the previous one, the right subtree's right was larger. But if you have, let's say, a zigzag where, let's say, the right subtree's left is bigger, or the left subtree's right is larger, we have to double rotate in those situations. So let's do some examples of when that can possibly come up. Let's go ahead and now another example here. Let's talk about this example. So I'm going to just zoom on this. Let's insert the following. So we're going to have 50, 25, 75, 70, 80, 20, 30, and 15. I think that's correct. So, all right, well, let's go ahead and do the same process. I'll do this kind of quickly again. So we first insert 50, height of 0, no problems there. Insert 25, left of 50, problems there. Insert 75, no problems there. And height, of course, should have been 1 earlier. My mistake on that. And then we're going to now insert, so we have 50, 25, 75, we insert 70 next. So 70 has to go over here. Height of 0, update the height to be 1, update that one to be 2. Again, there's no imbalances along the way up the tree, so we're still good. Then we insert 80, which is larger than 50, larger than 75, so 80 goes over here. This height will be 0. And all the heights up the tree will not change. Then we have to insert 20 next, and 20 would go over here. Height of 0, and this would be height of 1, and the parent or root will be at still at the height of 2. So again, there's no imbalances to worry about. And then we insert 30. So in this case over here, we have 50, so 30 would go over here. The height of 0. Return this height up here, will be 1. Return height up here, which will be 2. And we see an issue right here. So, maybe I made a mistake with this. I was hoping to have an issue later on. But anyway, okay, so we have an imbalance issue right over here. Because after we inserted 30, actually, never mind, my mistake. Oops, I made a mistake here. That's why. Supposed to be over here. My mistake. That's why it seemed odd. So this will be both 0. This will be 1. Okay, there we go. So that's the reason why I made a mistake. So there, after inserting 30, we have the following binary search tree. So now let's insert 10. So then inserting 10, well, it's going to go over here into this spot because 10 is smaller than everything else in our tree. Height we'll update the height to be 1. Then we have 2, we have 3. We notice again there's no imbalances to worry about. Everything is just fine over here. And then we're going to insert 15 at the very end. So 15 is less than 50, less than 25, less than 20, and larger than 10. So 15 goes right over here. So I'll zoom out just a little bit. 15 goes over here. The height of 0. Then return the height up. So 10 will have a height of 1. No imbalance. 20 has a height of 2. And we have an imbalance issue right here. Because right here in our tree, we see that, well, 20's left subtree has a height of 1. And the right subtree has a height of -1. Their difference is going to be 2. So we have an imbalance right over here. And since the left side of 20 is larger, we have to have a pointer that will point to that left side node. And we check, okay, so in this situation, we have it where the imbalance occurs. It's left subtree's right subtree is larger. So for that blue pointer, its right subtree is larger. So we have a zigzag situation over here. So for a zigzag, we have to do a double rotation. The first rotation is going to be done just to fix that zigzag problem, and a second rotation will fix the imbalance problem. So over here, I'm going to go ahead and just copy this. Down. So you first have to do a left rotation on this node 10 because we have this issue where it's a zigzag, so you have to first left rotate. And for this, it's pretty simple. As always, we're going to set 10's right pointer to 15's left, which will just basically set it to a null. And 50's left pointer, which was a null, is now going to point up to the 10. And 10's right is going to be essentially null. And we have return 15 and lift it up over to 10. So the result now is going to be, try to just, you can copy this again so I can just save a little time here. The result will be that 15 will go up above 10. So 15 will go over here, and 10 will go over there. And 10's height, of course, will be 0. 15's height will be 1. And now, that first rotation just fixed that zigzag problem. So we have this scenario. We want to fix it. So now we see that the imbalanced nodes, left subtree is bigger. So now we can do a single right rotation to fix this problem, to fix this imbalance issue. Let's go ahead and copy this one, and then we can hit the, do the following first. So we're going to have to basically set 20's left pointer to 15's right, which will set 20's left to a null, and 15's right will point up to 20. Return 15 up, and 20 will fall below. So then we'll have the following picture. Side over here. So what will happen now is 15 will, so we have 20 over here, so 15 will jump above right there, and 20 will also change as well as height, but 10 remains unchanged, so 10's height will still remain 0. We have to recompute 20's height, which will be also 0 because 20's left and right subtree are both empty, so it will be a 0. And then 15's height will now be 1, because the left and right subtrees 0 and 0 plus 1. And then return the heights up accordingly. And we see here we have no more imbalances. Every single level, the left and right subtree heights will be off by no more than 1. This is going to be our final product. This will be, let's go into an example of a left-right rotation. We simply have to first left rotate this tree to get the zigzag to now not have a zigzag anymore. Then right rotation, fix the imbalance. So that's pretty much that. Let's do one more example, which will be a right-left rotation. Then I can go ahead and sort of go over the proof for AVL trees, and we can be done with AVL trees. So hopefully it's not really too complicated of a topic. It's rather a review. Maybe you forgot about this from 302, so I just repeated just in case because we're going to use this concept for red-black trees. We have to, of course, revisit rotations and make sure we understand how this works. But AVL trees are kind of a little bit simpler, I believe, over red-black trees involving self-balancing binary search trees. So it's starting off with this one's kind of simpler. Red-black trees are a bit more, a little more complicated, not much more, a little more complicated than AVL trees. So anyway, last example. So we're going to now insert the following. So we're going to insert 50, 25, 75, 90, 70, 100, and 90. 71. Okay, cool. So now we have this situation. So let's go ahead and just insert these one by one. So 50 would go over there. So just a little quicker. 25 would go over here. We update the height of 50 to become 1 now. No imbalances. Insert 75 next. The height of 0. So everything is still fine. Then we insert 20. Goes to the left. There. We update the height up the tree. That. Then we insert 90. Height of 0. So it's going to have a height of 1. And everything else is still fine. So no imbalances yet. Then we'll insert 70 next. The 70 is going to go over here. So it's the right spot for 70. Height will be 0 because it's a leaf node. And all the parent nodes' heights will remain the same. Then we'll insert 100. So 100 will go over here. It's larger than everything in our tree. Update the heights up the way, and no imbalances happen anywhere. Every level, there's no imbalance issue to worry about. Then we'll insert 95 at the very end. And 95 would have to go over here. Height of 0. We're going to go ahead and return pointers up our tree. So we're going to have height of 1, no imbalance, height of 2, and we have an imbalance right there because 90's right subtree has a height of 1, and the left subtree has a height of -1. Difference will be off by 2, so we have an imbalance right over here. Detected imbalance right here in our tree. You have to maintain the, so in this case, the right subtree of 90 is larger, so you have to maintain a pointer that points to that node as well. And now the issue, once again, we have a zigzag once more because the left so we have 90's right subtrees, left subtree is bigger, so we have a zigzag, so we have to first perform a rotation to fix that zigzag, and then a rotation to fix the imbalance. So here, since 100's left subtree is larger, we have to left rotate this 100, which will basically set 100's left to a null because 95's right is a null. So we set this one to a null. And then 95's right will now be 100 and return 95, which will lift it above 100. Let's go ahead. Just, this. And move it over to the side a bit so I can, and I'll paste it over here. So what happens now is that the 95 will get lifted up above 100 as a result of this. Its height will be 0, 0, and 95's height will now be 1. So we fix that zigzag. Now we have to rotate this node essentially to fix the imbalance. So to do this, well, we're going to first set 90's right to set it to 95's left. 95's left is null. 90 will have a right child will be null. And then 95, which is going to be over here, we're going to set this pointer, its left, to point to 90. Return 95, so it's going to lift 95 up, and 90 and 100 fall below. Let's go ahead and just copy this. Ready? Done with insertions for right now. What happens now is 95 will move up, so let's erase all this to this. Picture here, 5 moves up. 100 still remains the right side of 95. The height of 0, that does not change. And 90 will fall below because we set 95's left to be 90. It's going to fall below. Recompute 90's height to be 0. 95's will be 1. Everything above, we don't have to update anything because everything will remain the same. And there we are. And now we have a balanced binary search tree once again. So we have left and right subtree heights will be exactly, well, at most, 1 off. So that's basically how that works. This is going to be an example of a left-right rotation. I'll put this over here. Left-right rotation. So basically, all we have to do is maintain these heights, and as we turn up the tree after insertion, we constantly check the left and right subtree heights, and we just have to rotate if at some point we have a case where the left and right subtree height differences is off by more than 1. So that's basically how we work with AVL trees. So I guess any questions on any of that? So I guess the last sort of topic here is going to be covering, I guess, deletion. So insertion was something that we probably covered in 302, and this is sort of review, but hopefully this review kind of helped you remember is if in case you forgot about AVL trees. So last thing I'm going to cover, I'll talk about deletions. I have about 10 minutes or so left, so I'll cover deletions next. And then I'll probably prove the height of an AVL tree. And then next time, well, I guess probably next time we'll first start off by going over the proof as to why an AVL tree height is always log of n. And then we'll go into red-black trees. Let's go ahead and just do deletion next. So let's go ahead and have the following binary search tree already constructed, just to kind of make things a little easier here. So we have 50, 75, 12, 7, 30, and 40. And we'll have 70 over here, 85 over here, and 90 over there. And of course, we'll have the heights. So we'll have computed. Of course, you would have updated these along the way, but I'll just kind of shortcut this a little bit. It's supposed to be 2. Okay. So we have this binary search. Here's AVL tree. So let's go over deletion again. So let's recap this. So let's go over how to delete. I want to delete 90. So remember, there's a few cases involving with deletion. So if we're trying to delete something with no children, it's a very simple case. So for deletion, we have to first find where is 90 in our tree. Using our standard binary search tree traversal, we can find that 90 is right over here. We just compare 90 larger than 50, larger than 75, larger than 85, so 90 has to go, 90 is going to be right there. So we found 90. So we check, it has actually no children. So a very simple process to delete 90. All we have to do is deallocate 90, return a null. So we go back up the tree, 85's right pointer is going to catch a result of null. So remember, whenever we insert, or I guess in this case delete, we return pointers back up to the parent node, and the parent node is going to catch that result. So we deallocate 90, return null. So other words, it's going to basically, I'll go ahead and I'll just sort of copy this. I'll just erase it right there. So we're going to go ahead and remove 90. But for note taking, I'll probably just redraw this that way. In case you're looking at the notes, all we have to do basically just move 90 just like that. And 85's highest will now be 0. We have to go ahead and move the tree, we have to go ahead and just update the heights along the way. And as we went up the tree, we did not find any instance of an imbalance. So since 90 only had no children, very simple, and removing a child, removing a node, could cause an imbalance potentially. So you have to rotate potentially on this case. Now right here we didn't have to because removing 90 did not cause any imbalance in our tree, luckily. So that's going to be our result after removing 90. So I'm going to go ahead and just write this here. Or actually, I'll just draw here's the resulting tree just like that. So that was simple. Let's go ahead and delete 12. So to do this, we have to again find where is 12 in our tree. So we compare 12 to the 50, less than 50, less than 25, and 12 happens to be right there. So in a case where we have want to remove a node, only one child, well, all we have to do basically is deallocate that node 12 and return its only child pointer up. So 25 is going to catch the result of that. So the result is going to be this. We're going to set 25's left to be 70, and we're going to deallocate 12. So basically, well, we first have to deallocate 12, or sorry, have to store 12's left subtree into a pointer, deallocate 12, return that left subtree pointer up, and 25 will catch the result of it. That's how we do it for a single node. So to do this, let's go ahead and sort of draw the resulting tree and update all the heights accordingly. So we're going to have the following. So we're going to do this. 70 goes up. 70 goes up, sorry. 7. The height of 0 moves up. And 25's height will still remain 2. And 25's left and right subtree height is not going to be, so it's going to be within 1. So 25's left and right subtrees are off by 1. So there's no imbalances here to worry about. So we're just fine at this point. So now let's go ahead and deallocate, delete 25. Here's where things are a little bit interesting. Delete 25. So once again, we have to go ahead and find 25 in our tree, and 25 is less than 50, and 25 happens to be right there. So you find exactly where 25 is. So for 25, well, it has 2 children, or 2 subtrees. So right here, we have a choice. Either we can actually find the in-order successor or in-order predecessor. So let's first do the in-order predecessor. So we have to go ahead and find the in-order. I guess I'll do in-order, actually successor. That's the simpler one. Which really means find the smallest element on the left subtree. Here, smallest on the right subtree, my mistake, smallest on the right subtree. So we'll do that. So in this situation, 30 is going to be the in-order successor. That's going to be the smallest on the right subtree. So all you have to do is go to the right and go as far left as possible. That's going to give us our in-order successor. You have to replace 30 with 25, essentially. So the steps we're going to actually do is the following. So I'm going to go ahead and do this a little bit more animated. We're going to have to basically take this and sort of remove it temporarily. So we're going to go ahead and store this possibly in some reference parameter of some sort. We're going to store this temporarily somewhere, returning null. So now 35's left subtree is now going to be 0. Now, if let's say 30 had some right children or right subtree, we actually would go ahead and assign that to 35's left side. But since 30 had no right subtree, then we don't have to actually do this. So we set 35 to be null because 30's right subtree was also null. And then what happens is we update sort of heights up along the tree. So as we move the tree, there's no issues with the heights. So now we go back up to 25, where we found the, that's where we wanted to delete initially. So we're going to go ahead basically and sort of update 30's left pointer with 25's left, and 30's right with 25's right. And then go ahead and deallocate 25. So end result is going to be, we're going to just remove this, put this right over here. Update its height to be 2. So all we have to do is go ahead and look at the node we're trying to remove. If it has 2 children, go ahead and find either the in-order successor or predecessor, and then we're going to have to replace that with the deleted node. And along the way, we have to fix any imbalances along the way because we did in fact remove that node from the subtree. So that could also cause imbalances to happen along the way. So we have to fix those. Now in this case, this is a very simple example, nothing to fix over here. So next time I'll go ahead and I'll sort of continue with this and then go ahead and find in order predecessor, which causes more problems actually. We'll go over that example, then we'll go over the proof for the height of AVL trees, and then we'll begin talking about red-black trees. So that's going to be it for today. So I guess take care, you guys. Stay safe. Thanks for watching. Have a great rest of your day, and I'll see you guys next time.